physics, in general, how everything interacts with each other in the world. It's a neat thing and can be applied to almost everything. To be more exact for my physics project, we're going to be talking about the violin. It's a weird how I'm not doing this as a presentation. But we're going to talk about more exactly the physics behind playing a violin. This mic is not real, just using it to grab your attention. Mainly what I'm going to talk about is Newton's second law of motion. To play the violin, you need to have a violin and a bow. Simple, and you hold the violin on your chin on the shoulder to stabilize it and drag the bow across the string. That's how to play the violin. But that's not what we're here for. You see, how the violin is being played is by the strings contacting the bow hair made of horsehair. A little fun fact. These two drag onto each other and produce a sound wave. How this is played is our main topic, friction. How we can see this in motion is to have a clearer picture. By that I mean what is the amount of force a violinist is using. So let's try to figure out the force of friction first, which is Ff. The weight of force when holding the violin is 3.1 to 8.4 kilograms. Let's say 7 kilograms for now. To first start, we need to figure out our forces. The forces that we have are the force of friction, force applied, force of gravity, and normal force. A lot to explain, but go down into simplicity. First, finding the force of gravity. So 7 kilograms times the gravity, which is 9.8, we get 68.6 newtons force of gravity. And the same number is applied to normal force due to it being a surface which the force equal out. Our next step is to find F net. F net is all forces combined, but can also use the equation of F net equals mass times acceleration. The average speed of a fast violinist is around 1.37 meters squared, which is around 120 BPM, aka the tempo. To go off topic a bit, tempo is the amount of beats per minute, which translates to the speed that each note is being played at. Back to topic. So 7 times 1.67 gives us the F net of 11.69 forces of Newton. Next is finding the friction, which is simple enough as F net times the coefficient of friction. For that, the coefficient of friction is two surfaces grinding against each other. This can be any two surfaces and they can vary. For my example of the violin and bow, the coefficient will be 0.8. So 11.69 times 0.8, we get 9.35 force of friction. Now for force applied, we simply plug this formula, making 9.35 negative to find the force applied, which is 21.04. For the average violinist, we could say that they play at a force of 21.04 newtons. Now for the other topics, why the tension of the string is important and how that can help create different sound waves. The force of tension is an object attached to a rope or string that's transmitted through the string as well as having equal or half and half depending on the amount. With violin strings, they have high tensions. However, they are at equilibrium. That means that the forces balance out and stay at rest. The tension of the strings vary from 39 to 83 newtons, but that's beside the point of what I'll be talking about. When you pluck the string with your fingers, also known as pizzicato, then energy in the string due to the high tension vibrates as it is able to make music. A few seconds later, it will go back to rest. This is generally how playing the violin works with the bow as well. There's not that much to talk about the forces of tension, as we already looked at Newton's second law, besides pizzicato. Spizzicato is playing the violin with the bow, but bounces off at each note. This also can be related to Newton's third law. For every action in nature, there's an equal and opposite reaction, such as the bow bouncing off the violin with each note. With these types of styles of playing and ways to use force on the violin, all comes down to the sound itself, sound waves to be exact. It helps with the pitch and tone of the music. Sound waves are waves of invisible energy that vibrates through the air. Reasons why we can hear these waves as sound is all in the ear. More in the inner ear. Your ear allows the sound waves to transform into electrical signals. It's weird, but more on sound waves. With sound waves, it comes in many different pitches that have higher or lower frequencies, or wavelengths. Long and stretched out ones have a more low and bass sound, while compressed ones have a higher pitched sound that we can't hear if it's at a higher frequency. How this contributes to violin is how the pitch can differentiate when you place a finger on the string, reaching higher pitches each time. Pretty neat, but you can also change speed and force of friction to get a type of tone from it. Well, that's all I got for now. I've already wasted around 4 minutes of your time, and it's late for me. Some information may or may not be true, but that's it. You can tell I have changed my appearance, so have a good evening and a good night for me.
I need some sleep.